Hello, everyone, and welcome to today's webinar, hosted by the American Rock Mechanics Association and specifically the Technical Committee on Tunneling. My name is Reza Hedayat, and I'm the chair of this committee. Today's presentation will be delivered by Dr. Zijin Zhang of Tongji University. The webinar, as usual, will feature a 40-minute talk followed by a 20-minute question and answer period or session. Feel free to submit your questions as they arise at any time using a chat function, but we will definitely have the option of going through the questions during the dedicated Q&A time. We ask the audience to mute themselves and use the mute option and be in the listen-only mode during the presentation, but we would welcome folks to unmute and have a discussion during the Q&A session. For those who are attending the live session and are interested in obtaining a professional development hour certificate, we have arrangements with Minds where you can submit a request to learn at minds.edu, and with a minimal fee of $10 receive the professional development hour certificate. It's my pleasure to introduce our speaker today, Dr. Zhang. Dr. Zhang is a tenured professor of civil engineering at Tongji University in China. He earned his PhD degree in geotechnical engineering from the China University of Mining and Technology. Professor Zhang's research interests include discontinuous rock mass mechanics, tunneling mechanics, underground structures, and construction. With over 30 years of experience in rock mechanics and TBM tunneling, he has served as consultant on rock stability issues for tunnels, dams, mines, and excavations worldwide. At Tongji University, Dr. Zhang has supervised over 20 PhD candidates and 70 postgraduate students. Notably, one of his PhD students received the prestigious Manuel Rocha Medal from the International Society for Rock Mechanics, ISRM. He has published over 200 papers in tunneling and geotechnical engineering and is the author of a textbook called Underground Structures. Dr. Zhang, it's a pleasure to have you, and I appreciate your willingness to offer this webinar at 10:30 p.m. Shanghai time. Please proceed with your presentation. Okay, perfect. We can see it in the presentation mode as well.
Okay. Hi, good morning, everyone. Thanks for the introduction from Dr. Reason. I'm Zijin Zhang from the Department of Geotechnical Engineering at Tongji University. Today, I will share insight on TBM tunneling in discontinuous rock mass, specifically focus on TBM block interaction. My presentation will proceed as follows. First, I will provide the background and the motivation for our study, then introduce object-oriented modeling techniques, followed by modeling procedures, identification of TBM-induced blocks, examples and discussions, and finally conclude with future research directions. Now, let's move to the background part. As you know, TBM tunneling in discontinuous rock mass involves significant challenges due to force and thrust. The rock mass behavior is largely dominated by these discontinuities and cannot always be simplified as continuous materials. This leads to frequent issues like cut height damage, face fallout, machine jamming, and inefficient support installation. In this slide, you can see scale effect in TBM tunneling. As you know, one of the theories to analyze the excavation stability of this continuous rock mass is traditional block theory suggested by Professor Richard Goodman and Dr. Dehua Shi in 1985. However, traditional block theory see the excavation area as a free space, but in TBM tunneling is confined by the cutter height and the shield, which change the dynamics significantly. Therefore, our research aims to enhance the understanding of how blocks behave during TBM excavation in truncated rock mass. As mentioned above, traditional block theory assumed free space during excavation, which suits drill and blast tunnels, but not for TBM tunnels. TBMs provide confinement through the cutter height and the shield, which restricts block motion and changes interaction conditions as the machine advances. So, block shapes, size, and interactions evolve during TBM excavation. The stability analysis for TBM tunneling usually involves two steps. First, we need to translate real-world fractured rock mass into digital virtual models like this. Second, we can use these continuum-based methods such as block theory or DM to identify unstable regions. In our research, we employ a morphological visualization method for block removability analysis as published in 2014 and 2020 to evaluate TBM block system stability. Here about the motivation. This research aims to capture the geometric and mechanical transformation of rock blocks during TBM excavation. Key tasks include first, dividing ground blocks into those influenced and uninfluenced by TBM. Second, further splitting influence blocks into contacting and non-contacting types. Third, defining subtypes such as front, corner, rear blocks of contacting blocks. Fourth, presenting identification algorithm for those blocks, then simulate machine block interaction. First, developing visualization tools and using morphological visualization method extended from block theory to evaluate stability of single or groups of blocks based on the code we developed, named as Block Lab TBM. Next, I will intro that platform in detail. Now let's move to part 2 about the object-oriented modeling ideology. So here, first of all, is about the object-oriented programming. You know, OOP is a programming paradigm that uses objects to combine data and behavior. In our context, objects represent real-world work features, complex data, and conceptual models. And here show you some key terms, such as class, instance, property, and method. About the object-oriented programming, which can offer modularity, treating both data and precise input. It simplified code adaptation, especially for GUI development. Inheritance enables efficient code organization, letting multiple class share trees from a parent class. Also, OOP naturally maps real-world phenomena, such as TBM tunneling. Then we can from a software. Here, we first analyze the real-world system, TBM tunneling. We build a conceptual model using object-oriented analysis, followed by an object-oriented design phase, which turns the conceptual model into program elements for simulation. Here, show you the procedures. About the object-oriented analysis of rock system, we produce a conceptual rock mass model, and each breaks down the system into objects such as blocks, drums, fields, etc. And then recognizing the necessary object and their network of relationships is the key. Here show you the details. And in this figure, we illustrate the complex relationships among rock system objects. Blocks are linked through bonds, boundaries, and the spatial relationships. Try to capture this network is crucial for accurate modeling. In this study, we use object-oriented design to turn the conceptual model from OOA into a structure suitable for programming. It brings analysis and implementation, enabling us to run realistic simulation on computers. Also, a universal class library for rock system models was designed for this research. It makes the model accessible and reusable for various engineering scenarios. In detail, we establish both global and the local coordinate system for the model. Coordinate transformations allow us to map between field measurement and the digital model, and maintaining spatial accuracy. Also, here show you the mathematical expression for converting points between the global and the local system, ensuring precise geometry during simulation. This class organizes the geometric data for analysis regions. For example, it can model a deep tunnel on a mountain slope like this, providing flexibility for different scenarios. About the geologic planes. So here, geologic planes represent boundaries, joints, and excavation phase. We can also model force with thickness by treating twin planes, by treating twin planes and inserting fragments, in between. And here show you the class how to generate size of subparallel joints with specific positions and the order.
Seems like we had the glitch and sharing is stopped. Would you be able to reshare?
Lisa, could you hear me?
Yes, I can hear you. I can see you. And now I see your presentation in the practice mode.
I'm not sure you can hear me or not.
Can you hear me? I can hear you very well and clearly.
Yeah, sure. I can hear you.
Okay.
And
And I can see your presentation, but not in the presenters mode. If you want to swap it to the presenters mode.
also I need to. So, let's see, I need to share the presentation.
All right, perfect.
Yeah, now it's okay.
It's perfect. Yes, please proceed.
Okay, sorry.
Yeah, that's it. Thank you.
Oh, okay. Here, so you can see this class generates size of subparallel drawings with specific positions and orientations, and the drawings can be infinite, truncated by boundaries, or simulated as disks of fixed extent. In this slide, randomly generates finite structures with realistic spatial distribution use position disk modeling, which mimics natural patterns. For example, here show you three sides of stochastic drawings which create a structure network showing how complex geometrical patterns can be represented in the model. For simplicity, the domain is first divided into convex element blocks. That means these serve as the modules building blocks. Then, by combining element blocks, we form complex blocks, which can be either convex or concave, more closely matching real work conditions. Here show you the excavation class. Simulates various excavation types such as tunnel, slopes, foundation phase, curve, excavation phase are approximated using planar physics. About the visualization manager class, you can see this class adjusts visual properties such as color, transparency, lighting, etc., so that the 3D model is clear and informative. Here show you the stability evaluation methods, like the still analytical or still graphical approaches suggested by us, allowing us to analyze block removability and stability. In particular, deep trend visualization sightings help us understand the rock system and its stability and the various lighting and the color schemes. So in this slide, we summarize the structure of objects in the rock system model. You can see from basic geometric data to complex block assemblies. So here it's a software show you how to construct a model. We need to prepare the necessary theory parameters. Then you can construct the model easily. based on your requirements. We can put different joints force, including their angle and orientation and the properties to this model. When we finish the construction job, next we can do the analysis job, such as the removability or stability analysis. So the accuracy usually depends on the parameters we input and depend on the the real life project investigations about the necessary parameters. So here show you how to construct a slope model and a tunnel model. Okay, so in these slides, you can see about the analysis part of TBM block system. So for TBM tunneling, blocky rock mass, we focus on blocks that are both geometrically removable and mechanically unstable. The progressive advance of the TBM continuously alters block topology and stability. You can see here the illustration shows the evolution of block stability during TBM tunneling. Stable blocks can become unstable as the TBM progress. Now let's move into identification of TBM-induced blocks. A novel classification method was created by us. Blocks are classified by their spatial relations to the TBM. In other words, the classification relies on the block's position relative to the bottom machine, which is practical for describing block behavior and interaction. In detail, blocks can be categorized into influence or uninfluenced by TBM excavation. Among influenced, in detail, classify them into contacting or non-contacting blocks. And the contacting blocks are further divided into front, corner, or rear blocks. Here you should note that block types can change as TBM tunneling proceeds. About the block characteristics, here you can see contacting blocks have a distinct geometric features. Rear and the corner blocks are always concave, and the front blocks can be convex or concave, depending on the presence of joint-formed concave regions. Blocks can also move by sliding, vertical lifting, or rotation. Our analysis checks which of these modes are possible for each block. We focus on whether blocks can be removed by translation or rotation. It is a key part of predicting potential hazards. During TBM advancement, cutter height and shield interact with the excavation phase, creating a complex system of force. Front and corner blocks bear thrust and torque. Rear blocks are more affected after shield passage. Clogging of the cutter height and the shield jamming are frequent issues caused by unstable front, corner, or rear blocks entering critical machine areas. So here in this table, we summarize the classification and the features of contacting blocks, highlighting their influence on TBM performance. Here, Visual examples of cutter height plotting and the shield jamming, illustrating the real-world impact of block stability on TPM progress. As the TPM advanced block tap stability and the geometry
Apologies, seems like we have had disconnection with Dr. Zhang. Would suggest resuming once he joins. So I'm going to pause the recording for a second and would appreciate your patience as he seems like to be here as well again. All right. Dr. Zhang, I think you're on mute right now, but we can see your presentation. Can you please turn on your microphone? I think you are currently on mute. Yes, perfect. Can you hear me? Yes, I can hear as well.
Okay.
I think if you swap your presentation, just use the top middle option. Usually that's where I usually switch to the presenter mode.
So the net problem is how about now?
We can see it in the practice mode. If you use the middle option from the top, yes, the middle one usually is where I can switch. I don't know the Chinese version of it, but yeah, if you can switch to the presenter mode, it should be good to go.
I need to share it again.
Okay. All right, perfect. Thanks.
Okay, how about now?
That's great. You can see it.
Oh, okay. Sorry for the net problems.
Oh,
And
that's all right.
so you can see as the TVM advanced block tap stability and the geometry change, a front block may become a corner, a rear block, and eventually be removed from the excavation phase. These figures show the progressive development and transformation of blocks at different moments as TBM moves forward. So here show you how initial front and the corner blocks can split, become unstable, and ultimately disappear as the TBM progress. By the end of the excavation, all influence blocks have been removed and the tunnel face is stable. Now let's move to part 4 about the modeling procedure and algorithms. So here is a short introduction about BlackLab, which developed by us. It's an object-oriented tool in MATLAB for analyzing block system using block theory and the visualization. BlackLab's graphic interface allows users to build, visualize, and analyze complex block systems easily. To identify influence blocks, we check for intersection between each element block and the tunnel parameter. If an intersection exists, the block is considered influenced by TBM excavation. The algorithm calculates whether a block face intersects the tunnel boundary, determining if the block is inside or crossed by the excavation. After identifying influence blocks, we cut them by the excavation phase and the tunnel parameter to determine their contact type, front, corner, or rear. These figures show the spatial relationship and the classification per size for front, corner, and the rear contacting blocks. So here show you a schematic shows you where active cutters contact a given block, citing the stage for force and the stability analysis. This slide shows you the normal and the tangential force act on the blocks from the cutter height. Their directions depend on cutter height, rotation, and the block geometry. In this slide, we define local and global coordinate system to accurately compute interaction force on the excavation phase. Here are the mathematical expressions for summing up normal and the tangential force over all active cutters, and for computing influence moments. Also, moments on blocks are computed as the cross product of position vectors and the force vectors for all cutters in contact. So about the interaction between TBM and the rock mass, we also need to consider shield block interaction. Usually, it becomes relevant when blocks fall into the shield. Until then, their stability is isons using block theory alone. Block morphology describes the shape, configuration, and the structure features of blocks. The analysis involves representing geological discontinuity and the characterizing block convexity and the removability. We only need to analyze mechanical force for removable blocks, front and the corner blocks, experience normal and the tangential interaction force. Rear blocks only after shield contact. This figure breaks down the components: active force, normal reaction, and the tangential reaction, showing how force interact to determine block stability. For rotational motion, the sum of external moment equals the sum of moment due to active force, including gravity and the cutter height interaction. So here you can see blocks can move by free translation, single plane sliding, double plane sliding. The conditions for each move are provided by the equations here. In the net active force, if the net active force has no opposing support, a block will move freely, detaching from the rock mass. If a block is pushed against a joint plane, normal contact force arises and the block slides along the plane. That means provided certain mathematical conditions. Here show you blocks may slide along the intersection of two joint planes if both provide supporting normal force against the determined by vector analysis. And this slide shows you the block rotation motion and its control equations. When the block rotates around a free corner, the equations here ensure rotation can occur only if specific conditions on force and the geometry are satisfied. Similarly, a block may rotate about the free edge if the side of inequalities provided here is fulfilled. About the block stability, so you can check by the sign of the net sliding force under conditions for a local rotation. Positive net force means movement, and the negative means stability. So here show you the details. And also here show you the control equations for rotation stability. I don't like to talk too much about the details. So as the cutter height advances and rotates, the block's geometry and the interaction force evolve. Active cutters and their influence units shift with each TBM movement. And during TBM tunneling, active cutters change as the cutter height rotates and altering block stability. Here we use the alterable key block concept to capture these dynamic changes, and the flow chart shows the alteration of block behavior mistakes induced by cutter height motion. Now let's move to the part 5 about the modeling example and the discussion. So let's move into a practical demonstration of our method using a detailed model setup. In this example, you can see we create a domain with diameters 50 by 50 by 50 meters. The axis S, Y, and Z span from minus 25 to positive 25, 0 to 50, and minus 25 to positive 25 meters respectively. Our tunnel with a 9.9 meter diameter is excavated along the y-axis from the origin. We simulate a double-shelled TBM, taking into account a slight over so the actual tunnel diameter is 10 meters. The TBM cutter height is equipped with 50 cutters. For modeling, each cutter applies a normal force of 100 and a tensional force is 10. The rock mass is set to a density of 2.1 power 3 kilogram per meter, which match typical geological conditions. In this table, you can see our domain contains 3 joint sides, each side consisting of 4 parallel joints, and these joints are parameterized by deep angle, deep direction, fixed point, and radius. For the details you can see in the table, this robust setup allows us to analyze TBM block interaction in a real-life multi-block environment. So once our joints are defined, the 3D block cutting algorithm generates convex blocks. So you can see here, these are the building blocks of our mechanical system. For major convex blocks, here show you 1 to 4 are created by the joint network. Each block's geometry is determined by the intersections of joint planes and the boundary planes. For example, block 1 is a convex block, while block 2, 3, and 4 are convex blocks also. Their exact positions are captured by vortex coordinates, and the relevant data for each is details in this table. These blocks serve as the primary focus for our behavioristic analysis. Each block will be tracked through the life cycle of TBM advance, such as analyzing how its geometry, stability, and the interaction with the machine evolves as the cutter height approaches, cause, and ultimately removes the block from the face. Now let's examine block 1 in detail throughout its life cycle. So here show you the initial stage T0 at the starting position. Block 1's location relative to the TBM is mapped out using stereographic projection. We can visualize its orientation and the drawings that define H. Here, show you the mechanical analysis. At T0, we calculate the number of active cutters in contact with block 1. For each rotation angle of the cutter height, we determine the direction and the magnitude of interaction force. That means both normal and the tangent. The equilibrium region diagrams allows us to visualize at which angles the block remains stable. About the kinematic analysis, the stability of block 1 is checked for all possible modes of movement, such as free translation, single plane sliding, double plane sliding, and rotation. The mathematical conditions for each mode are tested using the vector data for the block's fix. Here show you the calculation details. And this slide shows you the analysis results for single plane sliding and the double plane sliding. For the details will be given in next in table 3 and the table 4, respectively. The results show it's impossible that block 1 will move in the translational mode. So here show you the detailed results about block 1. Is stable in all translational and rotational modes due to sufficient interaction with the cut height. And this table also shows it's stable in all translational and rotational modes due to sufficient interaction with the cut height. About the life cycle behavioristic analysis, as the TBM advances, the block's volume will decrease. So when the TBM reaches 2.3 meters of advance, the number of active cutters contacting block 1 drops to 0 at some rotation angles. Here you can see the block is now alterable key block. It may become unstable and sliding along one of its planes if cutter height block interaction cease. However, the remaining volume at this stage is too small to cause TBM blockage or requires special pre-support. Then we can repeat the analysis for block 2. Now I don't like to talk too much about the details since the time is very limited. So here you can see the excavation period. At the excavation period, we track its relative position, volume decay, and the number of active cutters in contact. The block remains stable throughout its life cycle due to continuous support from the TBM cutter height, with no sliding or rotation expected. And also here show you the details for block 3. It's usually a non-conducting block, only entering the tunnel phase after about 19.7 meters of TBM advance. It then becomes a front block and later a removable block. And with respect to block 4, it remains non-contacting for most of the TBM's advance, then become a corner block at 41.12 meters. It splits into 2 sub-blocks. That means one becomes a rear block, the other a front block. So the upper sub-block is a key block, removable at 41.12 meters, but calculations show it remains stable and doesn't pose a risk of sudden movement. Now, let's move to the concluding part. So this work presents a novel method for block classification and identification in TBM tunneling based on an enhanced version of traditional block theory. By integrating object-oriented programming, we create a flexible modular software framework named as Block Lab that can efficiently handle project data, organize objects, and visualize results. The algorithm developed allow us to solve complex problems related to TBM block interaction, block removability, and stability. Our modeling example shows that this approach can predict and explain critical TBM issues like cut-height, corrosion, and shield damage, offering insight into how block transformation and the behavior affects tunneling performance in this continuous block mass. Now we are applying this methodology to some real-world TBM projects using field data to further validate and refine the models. We also plan to expand the algorithm to address more challenging scenarios in Sichuan-Tibet tunnels, such as extremely drunken rock mass, variable groundwater conditions, or complex excavation geometrics. Another area of future research will be integrating this method with real-time TBM monitoring system, combined AI technology, so that predictions of block instability can be made during actual tunneling, which can help engineers to take proactive measures to ensure safety and efficiency. Finally, while the current framework is powerful, we acknowledge its limitations, such as the computational demands of modeling very large domains and the need for more advanced ground propagation models. Addressing this will be a priority in future research. Thanks for your attention.
All right, thank you, Dr. Zhang, for the presentation. Really appreciate it. Now we have time for questions and answers. So I would like to invite the audience to either post their question or feel free to unmute so we can hear questions. And since I'm already unmuted, I think, Dr. Zhang, I do have one question for you.
Okay.
In highly blocky type of rocks or highly jointed type rock masses, I can imagine that it would be common to do pre-excavation grouting, or in advance of the TBM, with the inclusion of the probes, we can inject grout in an attempt to stabilize the ground. Are there ways that your model can essentially be adapted or revised to incorporate the effect of grouting?
Your question is about what? So
Grouting by injection of the cement or cementitious type mixes ahead of the TBM in an attempt to essentially minimize the permeability of the formations. Are there ways that you think this platform or this tool can be adjusted to include the effect of grouting?
yeah, TBM tunneling in jointed rock mass, usually it's very complicated. So it's better for the real time monitoring about the tunneling problems such as the jamming or the caused by the block. Unstable will jam, the TBM, move smoothly. So we have to do some analysis before the tunneling to predict, the potential, areas or potential, unstable blocks. Try to do some pre-support for this part.
Okay. Another question that comes to mind is how about the mixed phase situations or mixed phase situations where you do have a mixture of the rock blocks and maybe in transition to more soil deposit type formations? Are there ways that um, the tool can be adopted for that, like mixed phase?
Yeah, yeah. So we need to do some reinforcement job about the excavation phase. Yeah.
Mhm. Okay.
Okay.
All right. And I'm looking here. It doesn't seem like there is any question. So um, yes, I think there is a comment there. Yes, I think questions are coming here. We'll go through here. So Erica has any comments or knowledge of what happened during the recent tunnel collapse in LA? Are you aware
So
of the
so
recent?
here there's a question from the late listener. His question is about in the future version of the software, what will be the mechanism or boundary conditions to be considered to simulate water flow in rock runs? So it's a great question. In my opinion, we try to consider the water effect on the stability of removable blocks. blocks. So in some conditions, due to the water effect, some stable blocks may be, changed into removable blocks. So we have to consider this condition in the future. Okay, thanks for your question.
Dr. Zhang, there was a comment earlier. Are you by any chance aware of the recent tunnel collapse in Los Angeles?
What?
Have you heard or are you aware of the details of the tunnel collapse in Los Angeles?
Yeah, I hear some news through the internet, but I don't know the details.
Okay. All right. I think there is another question here. Douglas has said, it appears that reliability of the model is dependent on the density and quality of the geologic and geotechnical characterization of the rock to be penetrated by the TBM. Can you provide comments as to the necessity and the level of detail of rock characterization program?
Yeah, okay, it's a it's a very real life questions about the TBM tunneling. So about the density of the noise is an important factor. You know, during TBM tunneling, if the joint density is different, that means the removable blocks may be different, maybe larger or maybe smaller. So smaller the blocks, may cause some jamming problems, which depends on the open ratio of the TBM and the shield conditions So the density, you know, will affect, the number and the size of removable blocks. Okay.
All right, perfect. Any comments about the geotechnical characterization program? The second part of the question was if you have any comments about the details of the characterization program or any suggestions. I wasn't sure if Dr. Zhang has heard the question. But are there any additional questions or comments? All right, so I see none. I would like to thank everyone for your attendance and especially Dr. Zhang for his willingness to join us this late in his day to present. So quite excited to continue with the track of the offering of webinars. So please stay tuned for our next webinar, and thanks everyone and have a great day.
Okay, thank you.
Thank you so much, Dr. Zhang.
Okay,
Really
thank
appreciate
you.
your excellent presentation.
Thank you. Thank you so much.